ณะไหนคะ
Alright. So let's, I'll just leave you with 15 and then just to see how it works. But then, I mean, this age, hello everybody, sorry, I'm just talking. So, we can't, I mean, the bandwidth maybe we should choose optimally using cross validation. So as we have done before, but that I leave for you as an exercise. So that is one we have. So first, this is a 12. I think this with 3 that becomes a bit larger, but let's do it with 12, so that is what. Now let's do it differently. I want to do this time variation a bit more classical. In the sense that we have this series, so that's sort of at point time t. What I was doing is that I will actually now go on and then focus on a window of length, say 100, days, and I will do a rolling windows coordinates. So we basically use the 100 days till today, and then we will be so then go one step ahead, and then another one. So sort of this will be another one, and then we go one more day ahead, sort of moving. So it becomes a rolling window. That's very simple. Alright. And we do the estimation of the capital using OLS, but rather in a rolling windows setup. And that's pretty easy, and then we compare it. Because essentially the rolling window is also a very nice, simple method which is capable of capturing the potential variation of the data. But here it's not the case that we give dates, so to speak. If I have a window of time sort of horizon 100, then what happens is that all of the data before get a weight of 0, and everything afterwards get a weight of 0 too. Those that are in the middle can get a weight of 1. So that's sort of what I do here. Because, so what I did now with the another Watson, so the local linear, then I have a rating scheme that was so say that I'm at rank T, and we have a rating scheme which looks like this. So here are those points which are at rank T, and they get a bigger weight, and those that are back, and the weight goes slowly going up, so ahead and back. So as sort of you understood that the Kaplan beta seems to be very crazy. Goes up and up. So like it was minus 50. So that the average is negative, and so on and so forth. So well, the maybe one should use a kernel which is one-sided. These sides are 0. So that sort of you don't look ahead or rather backwards. Because if I'm at time period t, I don't have the observations ahead. So I have the observations back. And then this rolling window also takes care of this thing. We just look at the backward, right? Not forward. You can also have, of course, a window which is sort of like so, right? So 50 behind, 50 above, and then over. Okay? So let's do the rolling window regression 2 here. And that's pretty simple, indeed. And then we compare the two together. Now, let's start with rolling window here. Alright, so with a window length of, say, 100. Now we need the rolling alpha. We need the rolling beta. And then we keep the
can sort of easily plot. So that is what I want to do. And W are defined, so now we can do 4 observations in range of well, we want this to start at W and end at len of x. X we have defined already. Right. So and what I'm doing here is that, so let me write that. So let's say this is 100. Right? So that's observation number 1. From here on, then we have 100 observations. That's why I'm starting my loop. Starting from day, well, W with 100, and then going to the end. And that's sort of the indices that we look at. Okay. So that we have always all of those. So it means that the first 100 days and we don't have any data. But from 100 on, then we have, well, for the first observations, first basic unit, then we have 100 data points, and then we can do the estimation and go ahead. Alright, so that's why we do. So let's put the x in, or x in the window that we have. That will be x dot, so here we need an I log. And that starts from I, which is in the beginning 0, and then goes till so that will be I minus W till the end, till I. Clear? Well, let's call this T so that we have that's better. So you understand what I'm doing? Let's say I'm at period T, here's T. Alright. Then I go back from T minus 100 T. So then we have excluding T, so it means that we look at the dates before, right? Before, till yesterday. So that is the X, and now we do Y. That is Y, and let's call it Y in the window. Now we can do the OLS. So let's say I have a model, and the model is SM dot OLS, and Vin comes in, and then we need an SM constant on X in, and then we do a fit. I don't care about the heteroscedasticity because I want alpha and beta. I don't want to do tests. So that is what we have. Now we can collect the variables. So here we have the rolling alpha, which is model dot param dot alpha at 0. Then at 1 becomes the beta. Right. And then we have the rolling date, which is, well, that is the this is an atom. Well, that's a list. And we have to just append this. extra index active. So I have the dates. Good. So let's call it rolling DF. That's the data frame. So that it's easy to plot. Then the data frame coming from dictionary. Dictionary. And then let's sort of give them names. So we have the date. The date, which is the rolling date. Then we have the alpha, which is the rolling alpha. Then we have the beta, which is the rolling beta. Let's bring it here, and then we set the index to the column which is called date. Index, which is so it's not a function. It is column index. Okay. So that becomes a rolling bingo alpha beta. Rolling bingos. So sorry, these 15 minutes were not perfect. I do remember they were 11.
Index capable.
So this work. Right. so far we know 3 ways of estimating cap MD. OLS, using the whole sample, rolling window, and this localizing time. There is one other method, which I will tell you in the next few days. This work how does Kaplan alpha looks like?
You can hear this a little bit because you are this concept is
You see it's a little bit large, right? Well, that's not surprising. That's NVIDIA. Alright, so you're ready? Alright, so let's look at this. I mean, this graph actually seems not to be so much different from what we got from the when we use the localizing time, right? So in the beginning of the sample, Kaplan meter was around what OLS gives us, and then from around 2018, we went going up. Here we are rolling OLS. W is, that is what I used to could use an FSM. Or use it for. Let's maybe put these two estimates together. Yeah, so the localizing time and this one. So I will bring it here and put them on top of each other. So then what we have, let's run it. To look at them. Yeah, so this rolling window, well, it seems to, well, the orange is the local linear, alright? And then L is the orange. So now I want that to sort of regulate so that you already put this into my question. I just took the other one and then brought it here. So they follow each other. And you can part it. Fine.
Right, now I can ask my question. Look, the orange line, here you see around 2018, then there is a peak. Yeah? The orange line gets the peak faster than the blue. If I look at the orange goes up before blue goes up. Why?
Sensitive.
Sorry, this was a question out of view. But that's the point. This is a question about timing. So the orange one understands that you are getting into a more riskier situation faster than the blue. So sooner you understand. So the thing is that the blue one uses information in the past only. The orange one uses the past and the future. So and it understands, aha, so soon something is coming. So it reacts faster. So though it is interesting, but it's irrelevant for future understanding. Right? Because if I want to know now what will happen tomorrow, I won't be able to understand because I don't have the future information. Right? So though the pattern is okay, the orange and the blue actually follow each other. Right? So you have small cap M or something which is around 1-ish, 1.2 or so in the beginning of the time period, and then sort of it goes up and increases. Right? So both, so that's the pattern which we understand. Right? So NVIDIA has had small cap beta and then afterwards larger, and it's very similar to the framework. But the orange one is irrelevant for practical purposes because we never know future. But it uses future data. So just for you to keep in mind. Good. I think we are good for now. What you can do as an exercise is to do the following. The data, I mean, these are the returns, right? Sometimes they become very big negative. Sometimes they become very big positive, but they're very rare. So these events are different. And those are basically what we have. We didn't actually wipe out anything. So, now in the discussions that we had yesterday regarding the estimation at the borders. So I was saying that the borders where we have few data points and the confidence not generally are viable. So it means that, so if I'm going to do cap everything, then let's say I'm YT equals some 10x t plus b t into the diagonals. And I do a local union on this. So to speak, divided by h. So that is what we have. That was sort of what we did. So right now. That is what we did. Now we can actually define kt to be k as xt minus x divided by h. And they will be a little bit different. Right? So because we don't localize in time, but we localize on x. And the value of the market axis. So then the curve that we did, we thought we actually, sort of the function that we estimate will be not on time, but rather on x. And then here we will have m of x. Right? So which is expected value of y given x at a certain value of x. Let's say this. Then we will get some curve. So I don't, we can now go and estimate. Right? So that time dimension is not there, but rather than is x. This is a different question. So in this setup, I'm not interested in how beta changes in time, but rather I want to know how beta is then for a certain value of the market axis. So that would be a totally different question. So in that basic situation, then you have to, what you can do this estimate for all of the sample, but you have to be aware of the fact that the extremes, which are minus 10, minus 20, and so very large ones, will make this a strongly biased. That's a normal simply. Right? If you have very few strong outliers, so minus 10, minus 15, and plus 12, so very large ones, and you have some breaks, very deep market shocks, then this will actually give you very problematic, nonsensical alpha. Right? So or this problem that is sensitive to outliers will be highlighted here. And because you localize on a point for which you don't have observations. Right? And it means that so when you do this sort of estimator, you know the ends where x is very large or very small, right? And you will get very bad, nonsensical, as you say, coefficients. So then what you could do is that you could remove them from the sample. And that's sort of one way of one deals with outliers. So if there are too many, they are important, but then the focus is if you want to know sort of roughly how beta actually is sort of a function of, as a function of x actually changes on average. And maybe you should go on and then focus on the data points where you have a lot of them, not very few, one observation, and where we have say 40%. Or some other basically situations where you have very big or negative basically values. So then, I mean, here maybe you should indeed focus on x data, or all of the data that you have, on sort of a refined setup, right? So here time doesn't matter. So there is no importance attached to the x. Maybe you should focus on, say, 10% up to 90% parameters. So you remove the 10%, the upper and the lower 10% or 5%. Those basically problematic bits that you can remove. Maybe you can do a box plot, and then look at sort of the whiskers, and you identify the outliers and remove them, whatever else. And then do this rotation. Then you will get the function f, right, which is sort of you will get an alpha, you will get a beta, and beta is the derivative of m of x with respect to x, which is interesting. So that's the coefficient. So that's a capital beta localized on the x. And then look at it. Right? And you will potentially, you will not learn much out of this. I mean, on top of what one knows from the theory of finance. And let's say if x is very big negative, or if x is very big positive, then beta will be higher. So you are in love with values. But in any case, some information will come out of this. So that will be the magnitude that we can get. You understood? Right. That's an exercise. Okay? So you do it on your own. That's not hard. Just do a refine. Maybe don't do two things. First, leave all of the data so that you do the estimation, you say, aha, you get a beat of 60. Right, so it will be strongly actually moved by these outliers that you have. Or maybe remove them, and then do the estimation. Right. Or at least do the estimation on a mesh of x, which starts from the 10% quadrant up to the 9%. You don't estimate it for all, right? But rather in this range where you have a lot of observations. So do them both, so you see how it is. What type of alpha beta you get. That's also a fun exercise. So let's suppose the functional form of how kappa and beta reacts to x. So that would be a state dependent. Well, a state means what is the state of x, which is the acid return. A certain acid return, that would be the state. Let's say we have 1% increase, which will cause 1%. And how big beta is? How much does it actually the acid actually reacts to the two phases of the market. The market exists. Okay. So let me save this. And that is cap M. We are in day 4. I will post it. So we have half an hour before the next break. Let's do this exercise. So I want you to go out of the non-parametrics and go back to ARMA model. This special exercise with you, with the power scales and so on and so forth. And then you understand why OLS rejects. And then afterwards, after the lunch, then we do a forecasting exercise. Then we take an hour or so maybe on the forecasting exercise. So I'll tell you all the details and all of the diagnostics that you have. That's actually good, how to forecast. Like you yourself. So let me just remind you of OLS. Simply back to the simple things. So if I have an ARMA model, x equals the constant mu and plus phi xt minus 1 plus the R term by epsilon. By epsilon is IID. 0 sigma squared. Absolute value is small. And let's say we have a sample of size t on this process. It's very well. So part 3 actually says find asymptotic derivatives. So we don't do the derivations, but rather just remind you. So the square root of t times the hat minus the true parameter. This conversion distribution to a normal with v0 in the middle of the variance. That's 1 minus v0.
Yeah, 1 minus 1.
So then phi is a small, so phi is 0. Alright, and there is no zero correlation. If phi is 0, then this is off. So xt will be a simple shock. So that means that you get the estimator of this will be normal, this will be v0 variance. Alright.
the same time, then you have also a lot of problems. So when phi becomes 1, so when phi is 1, then this will be normal with mean 0 and variance equals 0, which is singular. That's just 0. So it means that this distance is so small that unlike the fact that you scale it up by square root of t, then you get a 0. Because when phi is 1, then you have an I1 process, and then phi hat minus t will be super consistent. So you see if phi is equal to 1, then you need phi something like so. You have to multiply by t so that you don't get a non-zero. So that was the super consistency from the unit process. So that you remember. If not, then we just. So here we are not here, rather we are in the nucleus section. But I don't care about the variance, just whatever it is. But let's say we want to do test. So we want to test whether phi is equal to say phi 0 against some alternative which is phi not equal to phi 0. So that's a terrifying part. So now, when you want to do that, then what is the process? When you write the values, so what you call it the p ratio. You estimate phi hat, you subtract phi 0, and then you divide by the standard deviation of the sort of what we know. So the standard deviation of phi hat, in this case, that's the variance, is 1 minus phi squared. So in this very simple setup, then we have phi hat squared, phi hat minus phi 0 under the norm, and this is 1 minus phi hat squared. Okay, so because we know the variance. But as I said, we don't care about the standard deviation. So now, if the norm is true, okay, so I mean the rejection rule was the following. Let's say we fix the type 1 error. You say alpha. Right? So that's type 1 error. That will mean that the probability that you reject the norm, so that's the probability under the norm. So you assume that the norm is true. Right? The probability that you reject the norm, which is phi hat minus phi 0 divided by sigma of phi hat will be bigger than z of alpha half. We converge in probability to alpha. Right? So, or we did not probability. We converge to alpha when t goes to beta. Right? That's sort of the test statistic sort of that we have here. Right. So that's essentially the size of alpha. Alright, so that's sort of what we have. Right. Now let's actually talk about the power. Alright, power of the test. So power is something that we calculate under the alternative. Alright? So how probably is it that we reject the norm if the alternative is squared? Alright? Now let's see how can we actually approach this. Is it okay if I mark here? Remember I'm telling you power, then Alright, so let's say that the norm is not true. Alright, so then we will reject. So specifically, let's say that the norm is like so. Some d divided by square root t. Where d is some number. Alright, so as you have the appropriate statement, so here I defined it to be minus 5
So five.
minus papa
So five.
to 5. Right? So that's a small mesh. Right? So that's the ordinary. Then this guy should understand that should be away from the job. So if I want to calculate the power, then I will basically do the following. Right? So I need the power function, we call it beta, and it is a function of t. And that's the probability to reject the norm if the norm is wrong. Right? So if the norm is wrong, then this phi0 is not phi0, but rather it is phi0 plus some beta. Alright? So that means that, so here, you have to go and calculate this probability of rejecting the norm with that specification. Right? But you can't put this square root t in it, and then you have that. And then let's see. So another variable that we have which we use to calculate the probability of rejection is this. That is what we have. So if the norm, let me write it now. Let's say the norm is wrong. It means we are under the alternative. Then the t ratio will be phi hat minus phi0 minus d divided by square root t. That is what we have here. And then divided by sigma of beta, that is what we have. Right. So let's see now what is going on with respect to all this sort of stuff that we have here. Right. So, well, I mean this guy, so let's rewrite this. That will be, well, I will multiply by square root t of phi hat minus phi0. Right. And there is a minus d. And then in the denominator, then we have the square root of t times sigma of beta. So that is what we have here. Right. We'll find. Another thing is that, so if I look at this sort of quantity, then the first term that we have there is what? The square root t times that is what I wrote here, right? So that should be divided by, divided by t. Sorry, so what is divided by t?
Yeah.
So that is what we have, right? So that's the usual second rule. You agree with what I'm writing?
Agree.
Right. So now let's see what is sort of happening. So instead of this, then I will put the quantity that I have, which is a square root of 1 minus phi hat squared divided by t. Alright. So that is what we have. Now let's continue. So that will be, well, this is a square root t divided by phi hat minus phi0 divided by square root of square root t and square root t cancels. And then we have 1 minus phi hat squared. So for the first basically term. Now minus d divided by, or this again cancels with that. And then we have a square root of 1 minus phi hat squared. Right? That is what we have. And let's see where does that converge. So in distribution, where is it? So let's use capital D. And that is converges in distribution. Where does this converge in the first term? standard norm. Let me be a standard norm 1, 0. Right? Because the numerator will be normal with mean 0, and variance 1 minus phi squared, and then with d escape. Right? So, thank you very much for that. Let me get a standard norm. And what about that? Then we will simply d divided by square root of 1 minus phi squared. So that's sort of what we do. So under the alternative, so if d is 0, if d is 0, if d is 0, then we are under the norm. Right? If d is 0, then we are under. So if d is 0, then this is off. If this is off, then we are under the norm and we are normal. If d is not 0, right, then indeed you get something which is a normal, where this mean minus d divided by square root of 1 minus phi squared at the standard level. That's a mean. So it shifts the mean minus d with the variance of 10.
Yep.
Right? Now let's look at the just reviewing stuff from your. Now let's look at these distributions. Right? So this is the standard norm. So this is some normal curve. Now if there is a d, let's say a negative d or a positive d, so say whatever we have. Let's say d is 1. Right? The minus 1. That doesn't matter. Say 1. And this is 0. Yeah. And let's say phi, the true value is let's see 0, right? Whatever value is. Let's say it is 0.1. That's the norm distribution section. So let's do so 1 minus 0.5 to the power of 2 becomes 0.25. That's 3/4. And this actually gives me minus 1 divided by the square root of 3 times 2. Alright. So 2 divided by square root 3. Let's do the calculation. This one that we have in number. Minus 2 divided by 20 sqrt of 3. This is minus 150. Well, roughly minus 150. So that means that we have now a normal which is here. This is 1, and this is 150. Now the standard normal curve, well, that's the same variance, which is here. That will look like so. Alright, the distribution is shifted. Right? So now if I look at this, so if I'm under the norm, so then this will be smaller to the black ratio. If this is negative, then we basically move. The black one is the distribution of the alternative. Now the rejection rule is that so if we calculate the d ratio, so here, let's say alpha is 5%. Alright. So that z of alpha half is 196. Alright, so here then we have minus 196. And then there we have plus 196. Such that the area that we have here is indeed 2.5%, 2.5%. So now under the alternative, when you go and also calculate the probability of rejection. Let's stretch this a little bit. Then we will basically see this. So that's the black line. And that is the input that we have. So that's how we reject the norm. Now, well, in these two black, if I put them together, that will be the probability that I will reject the norm. Let d is minus 115. Right? That is what you generally call the p-value. then that is what you generally call the p-value. The p-value is the smallest power under which alright, so maybe let's do the calculations. I just want to let you know what the p-value is. So here, so I have NP dot more dot what was PPF of that will be minus 196, right? We have to shift it to that side by this much, right? So that will be this minus that. And let's look at the positive side. No, it's not this, right? That is simple norm. I think I got it. PPF. Alright, so that's 85. Right, so 85%, 87, 88%. Right, so that will be the area that we have essentially. We could also calculate the area there, but I don't care. That's very easy. Alright, so if I look at this sort of areas, then I will have the probability that I reject the norm. Right? So then I have alpha 5%. Right? So that 1.96 that I use in my calculations actually comes from the fact that you have alpha to be 5%. So now I want that you do a little bit of a calculation. How much should alpha be such that I don't reject the norm? Well, here I reject the norm, right? I reject it. Because the probability is like 87 plus, so half a person, so 89%. That's sort of the probability of rejection. I don't want to do that. But now I'm actually asking another question. So the question is that how large? Well, if I change this for some other value, 10%. So if it's 10%, then this will move here. And we're 1.64. If I make it 20%, 30%, and so on and so forth, then this line will come back. Right? So there will be more probability of wrongly rejecting the norm, which is good. Okay. So, how large should the p-value be? How large should alpha be? Such that with these calculations, I don't reject the norm. Well, let me help you, okay? You don't have long. Let me right here, and this will be.
Check.
here we do the rejection. Right? So that is let's do it a little differently, okay? So maybe not with these numbers, those numbers are to do with Python, so that you could think, right? Let's say we want to test for this, right? So in general. And then we calculate the TS spacing and it becomes -3. And alpha is 5%. Alright, so alpha is 5%. Will you reject the no? If the TS statistic less than TS star, whatever alpha half is 1.9. You reject it. Why?
Very unlikely.
Very, what about 2 as a reject? You still reject. And I mean, the thing is that, so what you have, again, you have it in somewhere. So that's the standard norm. And then this is 1.96. This is minus 1. And let's say minus 2 is here. Right? And then you are saying, okay, now this is outside of the acceptance region, you reject it. So now I ask you my question again. How big should the p-value be? How big should the alpha be so that we don't reject it? Let's just stick here.
Okay. Yeah. So I'm going to you want to you don't want to reject.
Yes.
The alpha.
Yeah, exactly. So what will alpha be? Alpha is what? So that we don't reject. Here we reject, right? With that one. Very nice. How much? Well, just do the yes. Can be the norm. Let's go. I'm asking to tell you the function for the inverse beta. Understand all of that? Asking what is the inverse CDF of the standard norm?
It's don't inverse. I don't remember. Inverse CPF of standard form. We need just to see it. Alright, so that will be the CDF at -2 multiplied by 2.
If I was choosing alpha like so, maybe a little bit smaller, then I wouldn't have rejected very much. Now let me do another exercise. And now you know how to do the calculation. So that's the function. Norm CDF and minus something. So let's say I have half equals -1. This is t being -2, this is t being -1. Now how much your alpha should be? So you said it was bigger, sort of the smaller, as you said in the beginning. Now it should be larger. And what was the number?
0.317.
Right, so if alpha is like so, this be a statistic, then I wouldn't reject. The p-value is the smallest type 1 error for which the norm is not rejected. That's what p-value is. So this is a p-value. It has nothing to do with alpha that you pick. Type 1 error is something you choose in the beginning. When you start doing testing, and you say, okay, this is my decision. 5% is the probability that make a wrong decision. Now, p-value is the smallest probability that you do not reject the norm. There's the probability that you don't reject it. This is so 31.7. If I have alpha 31.7, then I will not reject the norm. And that is what we call the p-value. But it has nothing to do with how strong you reject the norm. It has simply something to do with the probability of rejecting or not rejecting a decision. That is the p-value. So it's the smallest size such that you do not reject it. You are not allowed to make any other interpretation of the p-value. That is it. So that's the definition, and you have to stay with it. You can't say that if alpha is 1% and your type 1 level is 5%, then you have a very strong effect. That's wrong. Just plain wrong. P-value is just there for you to decide whether you reject or accept the norm. That's it, nothing more. You never talk about the strong effects or weak effects depending on alpha. It doesn't make any sense. Because p-value is something else. So with these calculations, everyone will understand what p-value is. Time is over. Then in the beginning of the next section, then I will do this power curve. This one. So we see how the power curve looks like. So what is the probability of rejecting depending on the value of d? Well, obviously when d is large, all right, or large negative or positive, then sort of when things move, they go left and right, right? So when it's d is very negative, right? And the black one will go this way, really far away. Such that the probability that you reject will not becomes 1, because that's the very idea of the curve in the rejection region. On the other hand, when you have negative, so when this actually moves to the other side, then this black area decreases, becomes 5%, and then increases such that you reject it. With the rejection of the norm hypothesis, it happens because of a deviation to the mean. Mean is 0, but when you have a deviation like that, you will have a small shift to the left or to the right. So the distribution shifts, and then the testing actually principle that we have is that we compare these two distributions. Is the distribution black or blue? Put some probability in or some sample. So rejection group, whether this -2 is smaller than that, or bigger, and so on and so forth, then you start rejecting the answer. So testing principles from statistics just make a decision which is 0 or 1. Right? It doesn't say how strong the effect is or how weak the effect is. Right? There are two very good books on testing, but they are a bit graduate texts. If somebody is interested, drop me a message. I will not tell you, but rather I will tell you if you individually.